magnetic fields or not. So what I'm going to do now is I'm going to put this plate in between, and then I'm going to again put the currents in opposite directions, and so you will see the wires repel each other as if the plate were not there. 3, 2, 1, 0. There you go. So magnetic fields have a very interesting story to tell. However, electricity and magnetism are connected. How do we define the strength of a magnetic field? With electricity, we defined the strength of electric field in the following way. We measured the force, the electric force, on a charge, on an electric charge, and then the electric force is the charge times the electric field. That determined the strength of the electric field. Wouldn't it be nice if we could now say, okay, the magnetic force is a magnetic charge times the B field. So that would then define the magnitude of the B field. It would be nice. But as long as we haven't found a magnetic monopole, we can't do it. If you come with a magnetic monopole tomorrow, I can do this. But we have no magnetic monopoles. And so it cannot be done this way. How is magnetic field then defined? Well, it is defined in the following way. I take an electric charge, and the electric charge is Q. And if that electric charge moves with a velocity v, and there is a magnetic field where the electric charge is moving, then it is an experimental fact that the force is always perpendicular to v. If you want to call that B with a magnetic indication, that's fine. So there is a magnetic field, the charge is moving with this velocity, and there is a force on that charge which is always perpendicular to v. The magnitude of that force is proportional to the speed of the particle, and it is also proportional to the charge itself. If I double the charge, then the force doubles. If I double the speed, then the force doubles. And so the way that we define now magnetic field strength is this way. The force, and I give it a B to remind you, magnetic is Q, is the electric charge. Here is the velocity of the electric charge, the cross product with B. And you see that the force is always perpendicular to V, and that it is linearly proportional with the speed and linearly proportional with the charge Q. And this is often called the Lorentz force after the Dutch physicist. This equation is completely sign sensitive. If you change from a positive charge to a negative charge, then the force flips over 180 degrees. You change the direction of V, force flips over. Change the direction of B, force flips over. So it's a completely sign sensitive equation. The unit for magnetic field strength follows from this equation. This is newtons, Q is Coulomb, and V is meters per second. So this would be the unit for magnetic field strength, but no one would ever say that. In SI units, this would be SI units, we call that 1 Tesla, for which we write 1 capital T. A Tesla is an extremely strong magnetic field. The magnetic field of this magnet is only 2/10 of a Tesla, and that's a very strong magnet. We often use, therefore, a unit which is the Gauss, which is not an SI unit, but you'll see it often in books, and 1 Gauss is 10 to the minus 4 Tesla. The Earth's magnetic field is roughly half a Gauss. And so this magnet is about 2 kilogauss. But the SI unit is Tesla. If you look at a television or the screen of your computer, you have a fluorescent screen, and in a television there are electron guns that raster scan this fluorescent screen, On a television screen, you have 525 lines, and the electron guns scan that in 1/30 of a second. And the intensity changes of these electron beams create images. So if you look at the tube from the side, then there are electrons. One moment in time they may move like this, another moment they may be here in the raster scan. And so it's clear that if you bring a strong magnet in the vicinity of your television screen, that you will distort the image, because you are now affecting the motion of these currents, of these electrons. And there is a very famous artist, Nam Pike, who used this for his art, and almost every major museum in this world has a work by Nam Pike with distorted images using magnets and using television screens. I don't want to compete with Nam Pike, but I do want to show this to you. I have there a television set, and I have a very strong magnet, and I will try to distort that image and give you the best light that we know how to. And I suggest we try to find a program that we hate. So here is my magnet. Oh man, this is an extremely strong magnet. And let's turn on the television, and let's see what we can get first. Oh, I turned it off instead of on.
I'm a network validation engineer.
I am a CAD designer.
I am the super networking company.
The Sox owners are talking about manager Joe.
I don't think.
Neither do I.
Perfectly good writing.
I hate commercials. Let's go for a commercial. I hate commercials. Now watch it closely. Here comes my magnet. There's the image. You see that? Don't do this to your own computer, because once you have done this, it may never look the same. But these electrons now, can you see it? Can you see the distortion? Can you see the distortion? You're so quiet. Okay. So you've seen that. So you've seen that we can, with a magnet and a moving charge, that we can change the direction of the moving charge. Force on the moving charges. If you have an electric field as well as a magnetic field, then of course you have also